We're moving on to a new section that's going to take probably the next 4 weeks or so, and it's actually going to mostly be a new kind of algebra. So at school you learned a lot about the algebra of everyday numbers, and then during this course we also had a look at the algebra of logic, and this is going to be our third system of algebra called linear algebra. So we're going to make that a little clearer in a few days' time, but to start us off we're going to look at systems of linear equations. So the first thing we need to know is what exactly is a system of linear equations. Well, let's take it word by word. So we all know what an equation is. Really, it's something with mathsy stuff on one side and an equals and more mathsy stuff. So that should be fairly straightforward. The next thing we can think about is what is a system of equations. And a system just means probably more than one. So for example, you could have x squared plus 2y equals 3 and x is equal to minus 42, and together these two equations give you a system. So anytime you are solving multiple equations at the same time, it's a system of equations. So the final thing that we want to think about is, what does this word linear mean? And we'll make this a little clearer and more defined, but for the moment we're going to think about this as straight or flat. What am I talking about? Well, you're already very familiar with linear equations in 2 dimensions. You've got things like y is equal to 3x plus 2. Or for example, writing this slightly differently, 2x plus 3y is equal to 3. So these are both linear equations because they define the equation for a line. And in fact we can pop in a picture of one of these. So this photo over here is of this line 2x plus 3y equals 3. So this is where our idea that a linear equation is straight comes from. But we're also going to look at equations in 3 dimensions. For example, we could look at x plus 2y minus 3z is equal to minus 5. And if we plot that in 3 dimensions, because we've got 3 variables, x, y, and z, then what we get is not a line, but a plane in 3 dimensions. So here we've got, this is our x direction, that's our y direction, and that's our z direction, and this blue thing over here is the plane that goes through, that has this equation. And this is where our notion of flat comes from, because a plane is flat. It doesn't have any curves or bends in it. Just like a line is straight, no curves or bends. So the objects that we're dealing with when we're dealing with a system of linear equations is a bunch of straight or flat lines or planes, and in 4 dimensions or more. Also things that we'll call flat, although that's very difficult to envision. So you might be asking why on earth you need to know about these things. Well, it turns out that there are many, many situations that lend themselves to being modeled by a system of linear equations. And here are just a few examples. So this example is a fairly simple toy example. A grocer has coffee at some particular price and also some more expensive coffee, and she wants to make a certain amount of coffee that she can sell at a particular price, and you want to figure out how many pounds should be used. Now this is a toy example, but in fact many chemists when they are making solutions and things, use linear algebra, because this can be solved using linear algebra, as we'll see. Another example would be this one. Someone wanting to invest a certain amount in two different interest-bearing accounts and figuring out what would be optimal for them. So this comes up quite a lot in economics. And then another economics example is finding the break-even production level when you have a cost and a revenue equation. One final example, which is quite fun, is the idea of network analysis. So a network is composed of branches, so things like this, and junctions, and these can be used to model many things from economics, traffic analysis, electrical engineering, and others. And really what you're doing is you're modeling the flow through the various junctions of some particular thing. So for example, you might have a network that looks like this, and you want to work out. So we know that we've got, for example, 10 units flowing from 3 to 4, and so on. And what we want to do is work out what each of these flows is, or whatever it is that we're modeling. And it turns out that we can use a system of linear equations to solve this problem as well. So as we've always done in this course, we begin by mathematizing our ideas about linear systems. So remember when we talked about logic, we introduced a lot of new notation. There's not going to be much new notation here. It's more going to be the concepts. So firstly, we're going to define a system of linear equations. So this is a collection of a certain number of equations. So m really just has to be bigger than 1. And a certain number of variables, so n variables. So in our previous example, if you're looking in 2 dimensions, then you'll have n is equal to 2. If you're looking in 3 dimensions, then you'll have n is equal to 3, and so on. You can just keep going up. So what do these linear equations look like? Well, if we look closely at our first linear equation, notice that our variables only ever appear as themselves. They're never raised to a power, they're never square rooted, any of that sort of thing. They also each have some coefficient multiplying them. So this is a coefficient. And it's worth noting this coefficient could be 0. So in fact we don't have that variable contributing to the equation. It could be 1 or any other real number. So each term really just consists of a single variable multiplied by some number. And then we take a term for each of our variables and we just add them. So we don't have any terms of the form, for example, x1 times x2, no cross terms, so we don't have anything like that. We don't have anything of the form x squared or x to any other power. We don't have anything of the form x square rooted or anything like that. So every equation, and we've got m of them, has this particular form, but it's going to have its own coefficients and its own constant at the end. So if you see something like this, then you know that you're dealing with a system of linear equations. So now we've got a system of linear equations, we need to think about what it means to solve them or to find a solution. So a solution of a system of linear equations in n variables, where we've got, those are our n variables, is an ordered list of n real numbers such that if we substitute those numbers in, so we put S1 in for x1, S2 in for x2, and so on, then for every equation of the system, the left-hand side will equal the right-hand side. So what we're really saying when we're trying to find a solution is we get that x1 is equal to something, x2 is equal to some other thing, and when we plug these values into each of these equations, whatever we get, whatever number we get from plugging in, so we've got up to xn is equal to Sn, when we plug each of these s's in to the appropriate variable, it's going to give us something that equals the right-hand side, and that's going to be true for every equation. So usually we won't even bother writing these s's, we would just write a solution in a form such as x1 equals 12, x2 equals minus 7, x3 equals 2. Now it turns out that you don't always have exactly one solution. You might have many solutions to a system of linear equations. So we talk about the solution set of a system of linear equations, which is just every solution of the system and nothing more. So let's just firm up these ideas. So if we consider the following system, well, the first thing to do is to figure out how many equations. So this is, we've got m is equal to 3. We have 3 equations. How many variables have we got? Well, we've got an x1 and an x2 and an x4, oh, and there's an x3. So our n is equal to 4. So this is 4, you might be used to saying unknowns or variables. And if we want to think about our coefficients, if we go back to how we number these things, notice our first equation, each of the subscripts for the a begins with 1. So here we've got our coefficient of x1 in our first equation, so that's a11 is equal to 1, because there's really just a hidden little 1 here. Our second coefficient, so our coefficient of the second variable, a12, is 2. Now notice we don't actually have an x3 in this term, in this equation, so this tells us that the coefficient of x3 in our first equation must be equal to 0, and our coefficient for the variable x4 is going to be equal to 1. And then finally, our constant term for the first equation is b1 is equal to 7. And we could fill in, so for our second equation we've got coefficient a21, so this says from the second equation is 1, a22 is 1, a23 is 1. Now notice this minus sign here says that our coefficient of x4 in our second equation is actually minus 1, and our b2 is 3. And you could go along and fill in the remaining coefficients just to be sure there. So before we go on there, we can think about what solutions to this equation look like. So in order to have a solution, you need to have a value for each of the variables, which when you substitute it into each of the equations, makes them true. So I'm just going to tell you that x1 equals minus 2, x2 equals 4, x3 is equal to 2, x4 is equal to 1 is a solution. If you don't believe me, then what do? Well, you want to check that for each equation, so each of our 3 equations, if you substitute these values into the left-hand side, then you get the right-hand side. So let's just have a look. So if we want to check for our first equation, well, I'm going to substitute in minus 2 plus 2 times 4. Well, I don't actually have x3 appearing, so that doesn't matter. And then I've got plus x4. And let's check what this equals. That's minus 2 plus 8, so that's 6 plus 1 is 7, which equals the left-hand side. And if you plug these numbers in again in our second equation and our third equation, you should get that each left-hand side equals its corresponding right-hand side. You can also check that another solution to this is x1 is equal to minus 12, x2 is equal to 11, x3 is equal to 1, and x4 is equal to minus 3. And you should check that for yourself by substituting in. So it turns out that whether you have an example which has just 2 variables and 2 equations, or many more variables and equations, there are really 3 kinds of solutions that you can get to a linear system. And it's helpful to kind of have these 3 possible behaviors in your head. We're going to just look at 2 variable, 2 equation systems and see how they behave. So the first typical situation that we're going to have a look at is this example over here. Now, if you see x sub 1 and x sub 2, it might be looking a little unfamiliar. But if I rename x1 and x2 as x and y, you'll see that what we're actually dealing with is something that you've been looking at even at school. So if I put 2x plus 3y is equal to 3, and x minus y is equal to 4, then suddenly you can see that here we're trying to find, if we're solving these simultaneously, where these 2 straight lines intersect. So these are straight lines. And in fact, if I go ahead and I plot these 2 lines, then I've got this purple one is 2x plus 3y equals 3, and this black line over here is x minus y equals 4. And if we want to solve these simultaneously, what we're trying to find is any point which simultaneously solves this equation and this equation. And graphically what that means is we're looking for this point over here, which is the point 3 minus 1. So that's definitely a solution, and in fact this particular example gives us the typical behavior of having a unique solution. So the point 3 minus 1 is the only solution to this system of equations. Let's just check that 3 minus 1 actually is a solution. Well, if we plug 3 and minus 1 in, we've got a 2 times 3 plus 3 times minus 1, and that equals 6 minus 3, which is equal to 3, and that equals the left-hand side, the right-hand side. And if we plug in over here, we've got 3 minus minus 1, which is equal to 4, and that equals the right-hand side there. So this is definitely a solution. So one possibility when you're solving a system of linear equations is that you come up with a unique solution. There's only one value for each of the variables which solves all of the equations simultaneously. Our second example over here looks quite similar. In fact, our first equation is exactly the same. We've just done a little bit of a change for the second equation. And let's see what happens if we plot this one. So if you were to get a plotting program and plot this, you might get a bit of a surprise because it looks like there's only one equation. But in fact, these two equations model the same line. And in fact, you can see that if you divide the second equation by 2, you get the first equation. They really are just the same equation. And this means that for any value of x and y that you pick that satisfies 1, the second will be satisfied as well. So this, we have infinitely many solutions because every point on this line is a solution. So this is infinitely many solutions. So for example, let's have a look. So this point over here, which is the point 1.50 is a solution. We could have a look at this point over here. That's the point 0, 1 is a solution. We could have this point down here. That's another solution. That's going to be 4.5 minus 2. And any point that you pick on this line is going to be a solution. So far we've seen two possible behaviors for systems. You can have a unique solution, or you can have infinitely many solutions. And the final example that we want to have a look at is the case where you don't get any solutions. So we've got our same first equation over here, and we've tweaked the second equation just a little bit. And now let's see what happens if we plot them. Well, if you plot these two lines, here's our first equation, which is our purple line, and our second equation, which is this black line over here, is lying parallel to it. There is no place where they intersect. So this gives us an example where we have no solution. We cannot find a value of x and y, which if we substitute into the top equation, gives the left-hand side equal to the right-hand side, and if we substitute into the second equation, also makes it valid. And strange as it may seem, even if we go up to 15 dimensions, there are only 3 possible solutions, or 3 possible cases for solutions. So we have in fact seen all the options. For any system, doesn't matter how many variables you have, you only have 3 possibilities. You could have a unique solution, you can have infinitely many solutions, or you can have no solution. It's never the case that you can find for exactly 5 solutions, for example. If you find 5 solutions, that means you must be in the infinitely many case, and you could find many more. So what we're really going to be doing for the next couple of days is working out a rigorous way of solving systems of linear equations. So you might be used to solving, for example, 2 equations in 2 unknowns, and you can do that quite quickly, but we'd like to have a fast way of solving, for example, 4 equations in 4 unknowns. So that's what we're going to start with.